All right, welcome everyone to the inaugural meeting of the Applied Topology in Albany seminar for 2021. I'm very excited to have Hans Riess, who is a PhD candidate working with Rob Ghrist at the University of Pennsylvania. I'll mention that Hans started as an undergrad working with me when I was a postdoc at Duke, and I already identified that he was going to be a precocious and soon to be leading figure in applied topology. And I think he has lived up to those expectations and probably exceeded them.
You flatter me, Justin. Ignore all that, but
all right, take it away, Hans.
So today I'm going to be talking about what is essentially a categorification of cellular sheaf theory. And sort of the way I've structured this talk is I'm going to present a paper that Rob and I recently put on the archive. Well, maybe not so recently, but several months ago. And I will discuss a new theory of cellular sheaves of lattices. These are order lattices, not integer lattices. So they're post sets with least upper bounds and greatest lower bounds. And I'll go over all the basic details. But the picture you should have in your head, and I hope this video works, is that we have some network and we have things living above the nodes and also the edges of the network that describe discrete states. And these states take values in a lattice. And for the record, I did not make this animation. Anyone who knows my advisor will know that he is the one who made this animation. All right, someone in the waiting room, I'll admit them. Okay. So what are my motivations for even thinking about sheaves valued in non-abelian categories, like a category of lattices? Well, of course, the beginning of the story starts with Justin's thesis and Alan Shepard's thesis, which discretizes sheaf cohomology, one of the many things that Justin did in his thesis. But I'm interested in integrating this work with work by Marco Grandis that generalizes homological algebra, where by homological algebra, we very vaguely mean having objects and maps between them that boundary square to 0. And whatever boundary square to 0, that can be very general. For example, we don't need to have kernels and co-kernels necessarily. There's many frameworks we can work in. Mike in particular is very familiar with the Pupe exact framework. And in particular, Grandis sets forth a theory of cohomology for lattices in one of his books. I'm not sure which one. He has 2 books on non-abelian homological algebra. Then another motivation I had is sheaves valued in the category of sets, which Justin is very familiar with. Rave co-sheaves, for example. Merge trees can also be considered an example. And these sheaves are really nice, but they don't have a lot of structure to extract cohomology or some form of representation for them. So by adding additional structure, maybe we have hope to understand these sheaves better. And so examples include ones by Samson Abramsky and Goguen, as well as Rave co-sheaves. And of course, there's many other examples. And finally, harmonic analysis. What is a Laplacian? So the combinatorial Hodge theory of Ekman is just a very simple construction where, given a chain complex of inner product spaces, you can form what is called the Hodge Laplacian. And we'll get to all that. What is a Laplacian for a sheaf of lattices will answer that question. And there's also been recent work by Marcus Puschel in the sort of theoretical machine learning type community, defining a notion of convolution for signals that are supported on a lattice. And then finally, Jacob Hansen's work on spectral sheaves, trying to lift the theory of spectral graph theory to cellular sheaves. And more recent interest, which I'll give an example coming from this literature, is sets and relations. So you can form formal concepts, and there's this whole wide world of qualitative data analysis, which hasn't yet been integrated in applied topology yet completely, although there is some work by Michael Robinson that is in that direction. What is a lattice? As I said, it's a partially ordered set with least upper bounds and greatest lower bounds. And we say a lattice is complete if all meets and joins exist, so of all subsets of that lattice. And just for terminology sake, we say an element of a lattice Y covers another element if there's nothing in between. So on the right, we have an example of a Hasse diagram where we draw an edge in this diagram if the upper element covers the lower element. So this is a nice way of visualizing lattices. Now, Galois connections are a particularly nice type of map between lattices. So a Galois connection is a pair of order-preserving maps such that we have this adjointness property. And if you think of this lattice X and Y simply as categories, with the usual notion that we have a map from A to B, if A is less than or equal to B, or rather an arrow from A to B, then really a lattice is just a small category that's a post set, but also has limits and co-limits, which limits correspond to meets and co-limits correspond to joins. Hey, Yuli. So an adjunction between two lattices is exactly what a Galois connection is. And from what we know about adjunctions, we know that left adjoints preserve co-limits and right adjoints preserve limits. So we know that these lower adjoints in a Galois connection preserve joins. And we also know that we have a co-unit and a unit associated with an adjunction. And in a post set category where Hom sets are either 1 point or nothing, then we actually, these two properties that F lower, F upper is greater than or equal to X, these two properties below actually suffice to show that this is indeed a Galois connection. So here's an example of a lattice that is derived from a Galois connection of a simpler lattice. So these are called concept lattices or formal concept lattices. So given a binary operation, binary relation on two sets, X and Y, so we can think of X as a set of objects and Y a set of attributes. Maybe X is patients and Y are conditions that each patient has. Then there is a Galois connection, R lower, R upper, between these power sets. And power sets are indeed lattices, just taking the join being the union and the meet being the intersection. And we can form this Galois connection, as you see. and you can check this as a Galois connection. And the definition of a concept lattice is we consider the fixed points of the unit or the co-unit of this Galois connection. And this is a formal concept lattice. And how does this actually work? So we have this sort of binary relation. We have a bunch of objects and attributes A, B, and C. And I'm actually going to consider the unit. So I'm going to apply our upper first and then our lower, because we have less things to deal with. We have 4 numbers and 3 letters. And what we get by finding the things that are fixed, we get the sublattice of this power set lattice. And it has all these elements in red. And it's important to note that this, I said a sublattice, but it's not actually a sublattice. It's a subset that's a lattice in its own right. But for example, we don't have the join of A and B is not in the lattice, but we do have a join of A and B, and that's ABC. So it's a subset that's a lattice in its own right, which I kind of coin a quasi sublattice.
Hans, can I ask a quick question?
Of course.
So just to make sure I understand this example, so we sort of identified BC as sort of a simplex attribute space because there's patient 2 who has both conditions B and C, right?
Right, exactly.
And
so we think of I don't know if I can draw. I probably can draw on this thing. Yeah, I can. So I'll go back here. So we first look at the empty set and the empty set of attributes, and that sends everything to 1, 2, 3, 4. And as we see, there's no attribute shared by 1, 2, 3, and 4. So that goes back to the empty set. So that means this is a fixed point. Then we start with B. We look at the objects shared by B. We get these 3 guys. And then we look at attributes that are all shared by these 3 guys. And we just get B. And we do the same thing for all possible subsets of A, B, and C. Is that clear?
Yeah, thank you. That's much better. I think it was just going quickly back and forth with the upper lower and trying to identify fixed points was maybe a little faster.
Right. Yeah. So I mean, you probably I didn't give everyone enough time to see this definition, but this is just the things, the attributes that, so this sigma is a subset of X. Subset of X. All right.
Thank you.
So yeah, we do get a lattice, and actually in this case, it actually has a name. It's called N5, and it's, fun fact, the smallest lattice that is not modular. So we get actually really interesting examples of lattices this way. And I'm sure there's a representation theorem out there. What lattices can we recover by this construction? And then I guess my second favorite example of lattices that kind of come up pretty naturally is lattices of subspaces. So we have a vector space. Each subspace is ordered by inclusion, and the join of 2 subspaces would be the vector space sum. So if we take this vector space X, which is a line, and this vector space Y, then their sum is the entire plane. And we see that here. But the intersection of these 3 subspaces is just a single point. So we get this lattice with 3 incomparable elements, and then a top element and a bottom element. And my reasoning for or my desire to think about these lattices is that whenever we have a cellular sheaf, which is just, let's say, a network or a cell complex, but over each node of the network, we have a vector space, and over each edge, we have another vector space, and we have linear maps between vertices and edges, then we can pass to a sheaf of lattices, where over each vertex, we have a lattice of subspaces, over each edge, a lattice of subspaces, and we have a Galois connection induced by this linear transformation. And I think, as an exercise, people can think about what that Galois connection is. It's pretty simple. And so just for more formality, I'm going to introduce a category of lattices.
All right, sorry, Hans. So the Galois connection, is that the one, like you were saying, it's induced basically by the structure sheaf, like the maps or what?
Yeah. Yeah.
Okay.
Yes. So formally, we want this category of lattices, LTC, and this has objects, lattices, and morphisms, Galois connections. And we can compose Galois connections just by composing the lower adjoints and then composing the upper adjoints, but in reverse order. And I might skip this, maybe not. I just wanted to make a remark that adjoints are computable in the case of lattices, and in that this follows from what is really the adjoint functor theorem, but it's quite simple for lattices, that you have this explicit formula for computing an adjoint. Once you have, a lower, a F lower, then you can compute F upper pretty easily. And I just wanted to throw this out there that if anyone is interested in order theory, I haven't really found anything that characterizes this computation as far as how easy is this to compute. But I'm going to kind of skip through this to go on to the heart of things.
Was that last equation for the computing the adjoint, like with respect to the join, is that at all like related to convolution? Because it kind of looks like a convolution.
This equation right here?
Yeah.
Good question. Well, it is and it isn't, because we're not really convolving with anything. What we're really doing is we're taking a sub-level set of F and then taking the join of that sub-level set.
Gotcha. Yeah. And for convolution, there would be like another thing you would be multiplying it with. Right.
That's a very interesting comment. Yeah, thanks. Okay, so cellular sheaf theory. We start with a cell complex, maybe just a graph like we have here. And we have what is called the face relation poset, where we have vertices including into edges, the thing that most of us are extremely familiar with. And a cellular sheaf, or a Tarski sheaf, is just a functor. And you might ask, is this really a sheaf? And of course, this functor is actually not a sheaf, but if we just consider maps that go in one direction in each Galois connection, then we do indeed get a sheaf by the construction that a lot of you are familiar with, taking the Alexandra topology of this face relation poset and then extending everything. So in fact, we really want to consider, given this Tarski sheaf, which is takes values in this category of lattices and connections, we want to, each connection has a lower adjoint and an upper adjoint. We want to pick one of those maps in order to form nice limits. So if we pick the lower adjoints that are going to be the ones that are going forward, we get a sheaf valued in lattices and join preserving maps. And if we put the maps going backwards, we get a co-sheaf. And let's say we pick the maps going forward. So we have a category of lattices and join preserving maps. Then we can define our global sections as we normally do. And they are just assignments of data, or to be precise, they're going to be cochains, such that there's agreement when we push data along an edge to two vertices incident to an edge, that we have exact agreement here. And I would like to remark that it's really simple to compute this in the abelian case, to compute global sections, because if we want to solve this equation right here, we can just subtract this side from that side, and we end up taking the kernel of the appropriate matrix. And that's really how we compute cohomology in degree 0 in the abelian case. But now we don't have our minus sign, we don't have subtraction, we just have lattices. So at this point, it's not clear, how to go forward. But one way you can go forward is to define a Laplacian. So a Tarski Laplacian is an endomorphism on the 0 cochains of a Tarski sheaf. And it's given by this funky formula over here. And I'm going to explain what is happening. So maybe it's best to think about this all in degree 0, where we have vertices are our sigmas, and then our edges are our tals. So we start with a sheaf over this very simple looking graph with one bend. And we have data over all the vertices, and that's a 0 cochain. Then we apply our lower adjoint restriction maps and push that data to the center. Once we have done that, then we take the meat of the data we pushed over here with the data we pushed over here. Then we use our upper adjoints, the F uppers, to pull that data back to the vertices. And then finally, we take a meet again for what we've pulled back. And one way to really justify why this is a Laplacian is, and I didn't make a slide for this, but you can decompose this formula into two parts. One part I would call a expansion term, where we have an upper adjoint of sigma tau composed with sigma tau, and not another cell, but the same cell. So we have an upper adjoint composed with its lower adjoint, and we get, by the co-unit property, we get an expansion term. So this is the thing going on where I take something here, I push it, and then without taking a meet, I pull it back. And so essentially you can do this because upper adjoints preserve limits. So we can take this me and put it over here. And so the nice thing about the Tarski Laplacian is that we can indeed compute global sections with it. So if we start with the Tarski sheaf, then we have that the fixed points of the Tarski Laplacian meet the identity is the global sections. And that's a little cumbersome, but maybe the best way to think about it is the global sections coincide with this post of L, which are all zero cochains, such that when you act on them by the Laplacian, that you go up in this lattice of zero cochains. So you have this inflationary property. All right, so let's go over, if everyone understands what this theorem is saying, we can go over the proof, if that's okay.
Wait, sorry, I missed what is gamma of XF?
So gamma XF are the global sections of this sheaf. And I can go back to the slide where I define that. Here, this thing.
Okay, thank you.
All right, so we're trying to show that.
Oh, and sorry, you're taking the meat of two maps?
Yes, meat of two maps. So we take the meats pointwise.
Gotcha.
Yep. That should have been explained. Sorry about that.
Thanks.
I guess this, so Hans, can I just, do some foreshadowing of how this might work?
Yeah.
Right. Okay. So first of all, for everyone, global sections, you should just think of as consistent choices of data all across your network. So like if you like transport using the maps internal to the sheaf, you'll get the choices you made on higher simplices. But then I guess this this fixed point of L meet the identity. So that almost kind of feels like an equalizer condition, which is ultimately the sort of analog of kernels when you can't use minus signs.
Yeah.
Yeah. All right. Cool. Thanks.
There isn't an equalizer in the proof, but I'm sure you could write it that way. The proof is very simple and, in my opinion, kind of beautiful. As everyone learns in their undergraduate, first course with proofs, that to prove two sets are equal to each other, that the best strategy is to prove that one is a subset of the other and the other is a subset of the other. So that's what we're going to do. So first, we're going to suppose that X is a global section. Then what does this mean, just as Justin said? Oh, and we're only working with basically the one skeleton of whatever X is. So we can just think of X as a graph, and we don't lose anything. So for every one cell, which is just an edge, VW, being a global section means that you have agreement over this edge right here. Okay, well, what does that mean? That means, I'll flip back here, maybe you can't, but that means that if we look at, this is what the Tarski Laplacian is, all these terms in here are the same. So we can choose our favorite term, and that would just be F lower V including into E. Okay. Then the co-unit property implies, and I think I'm missing something, but no, sorry, I'm not. It implies that F lower of this is greater than or equal to X, and the indices on here are messed up, but you should just think of this as the same as this. So this term right here is greater than or equal to X sub V. And so this means that if each term is greater than, then the greatest lower bound is also going to be greater than X sub V. And therefore, this means that L of x is greater than or equal to x sub v. Okay, ready to go to the other direction? I didn't hear any objections, so now suppose that we're yeah, this notation's a little messed up too, but suppose that we're a post-fixed point of the Laplacian, so that we satisfy this fixed point condition in the theorem slide two slides ago. Okay. Then what does this mean? This means that this term right here, which is the inner term, this is going to be greater than the greatest lower bound of this term, which in turn, by our assumption, is greater than or equal to x sub v. So then we can use the property of being a Galois connection, and we can make the switcheroo where we move this over here. See how that worked? Because F upper is adjoint to this F lower. And this implies that we get that this term is greater than or equal to this term. And this is true for every single edge in the network. So we also get the opposite of this by just starting with W, which is the other vertex in this edge. And we get this other direction, so both get you equality and you're a global section. So this this notion of a fixed point, that a fixed point theorem for global sections really prompts a definition. And this definition, and maybe I haven't done much with this definition yet, but we can define cohomology as the cochains, such that when we act on the cochain, we move up in the lattice of cochains. And in degree 0, this is just the global sections, that the Tarski cohomology by definition, or not by definition, but by the theorem, is the global sections. And that's what we have in the abelian case, that cohomology in degree 0 coincides with global sections. In particular, if we're working with a Tarski sheaf where every stalk is a complete lattice, then we have that the Tarski cohomology is also a complete lattice. And this follows from this folk theorem, often attributed to Alfred Tarski, Nastor, also Dana Scott. But this theorem, and I didn't make a slide for this either, but it just says that whenever you have a order preserving map from one lattice to another, and we have, or one lattice to itself rather, so we have an order preserving map from one lattice to itself, and this lattice is complete, meaning that all joins and meets of all subsets exists, then the fixed points of this map form a complete lattice. So we get that cohomology is not only a lattice, which is nice, but also a complete lattice.
Sorry, Hans, can I have a quick question?
Yeah.
When you're going through your proof, I then realized I didn't fully understand how you were defining TH0. So can you go back a few slides?
Yeah, okay. So I probably should have included probably should have put this slide before this slide, I think.
Hmm.
That's probably the issue. But all I'm saying here is that post of L is a subset of gamma.
Okay. So post of L being the inflationary elements underneath this ladder.
Yeah. So post of L, so TH upper 0 is the same as post of L0. It's just a definition, TH0.
Okay. So that you're defining that way. You're not necessarily saying that like here's this like principled notion of cohomology that works in non-abelian categories, and let me use it.
Right.
Okay, all right.
No,
Instead
I'm not.
coming up with a definition that's
I'm coming up with the definition based on the fixed point theory of the Laplacian.
Yeah, and then maybe skipping ahead a little bit. So here you're relating it to this sort of sheaf that's naturally associated to your Tarski sheaf. And then so there, it kind of begs a question like, is there a notion of Tarski homology?
That's a really good question. And I think there is. So if you remember several slides ago, that we have this, whenever we have a functor into this category of adjunctions, that we can choose either the left adjoints or the right adjoints. So if we choose the right adjoints to be the maps that go forward instead of the left adjoints, then our Tarski Laplacian is the same, except for we replace meets with joints and we replace upper adjoints with lower adjoints. So there's this duality. And then in that case, I think you would be reasonable to say that Tarski homology is, instead of the suffix points or the inflationary points, we think of the deflationary points of this Laplacian, this dual Laplacian.
Yeah, cool. Thank you.
Yeah. And just to sort of hammer this home, why is this a categorification of the Hodge Laplacian of a cochain complex? So we start with a cochain complex, and maybe this is the cochain complex that we get from a cellular sheaf of, let's say, vector spaces that have an inner product on them. So in that case, all these co-boundary maps, they have linear adjoints. And so the combinatorial Hodge theorem says that the global sections, or rather the fixed points of the identity minus L0, or more familiarly, just the kernel of L0, is isomorphic to the degree 0 cohomology of this chain complex. And it's actually true in every degree that we can, that's what the Hodge theorem says, that we can identify the kernel of a Laplacian in whatever degree with the cohomology in that degree via this isomorphism. But a categorified version of this is we consider the fixed points of identity meet L0, which, remember, these are just the inflationary points. And that coincides with the global sections.
Sorry, Hans, this is a really stupid comment. Yeah, no, I guess you did have this equal sign, sorry, the minus sign in the right place. I was just trying to figure out, do fixed points of identity minus L0 correspond to like L0 of X equaling 0, quote unquote. So just getting that kernel.
Yeah. That's a good comment. That, yeah, I should have made that comment, but yes.
Well, I was for a while like convinced the minus sign should go the other place, but I was wrong. So
Yeah,
Can I ask an uninspired question?
of course.
I don't understand why that's the kth cohomology in that bottom line.
It shouldn't be. That's a typo.
Is that
I'm
0?
sorry. It should be 0.
Oh, okay, thank you. That
I'm so
helps.
sorry. Thank you for pointing that out. Okay. So in the case of the Hodge Laplacian, we have diffusion dynamics or harmonic flow. And that is determined by a differential equation, the heat equation. And we have a combinatorial version of the heat equation. And this is one way, if you have, for example, a bunch of robots and they all have various headings and they form a network. Some of them can talk to each other, others can't because of distance or whatnot. Then by applying this Laplacian, you can reach a consensus heading so that all the robots have the same heading. And this is like a message passing scheme. But a fancy way to say this is that we have this heat equation that is determined by the graph Laplacian. And so for the Tarski Laplacian, we have a similar thing going on where we can apply our Laplacian, meet the identity. So this is just L of x meet x. And we can keep applying that. So we start somewhere in our 0 cochains, and then we keep applying the Tarski Laplacian. We keep applying until we reach a fixed point. And one thing you can check is that if every stalk of our Tarski sheaf satisfies this kind of, not really technical, but kind of silly condition, which is that every chain in a lattice or poset, every chain terminates at some point, in particular, every descending chain. So if we satisfy this very, weak descending chain condition, and everything is finite, so if the number of K cells is finite, or the graph is finite, then there's some time horizon such that when we keep applying the Laplacian, we'll reach a cohomology class or a global section in degree 0. And this, another way to write this is we have a discrete time system like this. And for the Hodge Laplacian, we have this continuous time system, this is just the heat equation. And of course we can, discretize this using your favorite method from your undergraduate ODE course. But this converges in the Hodge case to the orthogonal projection of our initial cochain. In the case of lattices, it's not as nice, and we don't really have a characterization of where you're going to converge. We can say some things like if we start at the top element of the lattice of 0 cochain, so that means over each vertex, we have the top element of our lattice that will flow to the top element of our lattice of global sections. So that's one thing we can say. But we don't have a notion of an inner product in the Hodge theory case. And so I'm sort of going to, show this animation that I actually made this one. Rob didn't make this one, showing what the Tarski Laplacian is doing. So we have a network and a plethora of lattices living above the vertices on this network. And there's also hidden ones on edges too. And let's just take a look at this, these two edges in the bottom left-hand corner. If we zoom in, we see we have lattices over the vertices and lattices over the edges. And in fact, we have these restriction maps. And these are the lower adjoints that take data over vertices and they push them to data over edges. And not shown are the maps that go the other direction, because there's only so much you can show without your brain, you know, saying what the heck. So we start with an initial cochain or an assignment of data to each vertex of this graph. So we choose the top element of every lattice. Then we ride these restriction maps to the edges and we take the meat of these two things. Then we can pull back everything with our upper adjoints, the maps that go from edges to vertices. So we pull them back and we take a meet again. And then finally, we push everything back again, take another meet, pull back again. And now we find we're actually have a global section because we hit the same lattice elements that live over the edges. Let's look at that again. So we've obtained a global section. This is sort of a very little justice is done to this part of our paper, but I just want to say that there's another, version of a Laplacian for a Tarski sheaf. And this Laplacian comes from not a bona fide chain complex, but something like a chain complex, and defines cohomology in a more traditional sense and not just from the fixed point theory. And we get formulas for these Laplacians that are very similar, but we get joins here instead of meets. So there's a little bit of a difference there. But I don't think I have time to go too much into this today.
Right. What's pre? Just so you can.
So posts are the inflationary points. Pre are the deflationary points. Yeah.
Cool. That's what I was hoping you'd say.
Yeah. So this is kind of like a duality as well, but so if we go back, I don't know if I want to go back, but when we have our ordinary Hodge Laplacian, where we take the adjoints of the coboundary maps, we get this decomposition into a upper Laplacian and the lower Laplacian. So the upper Laplacian is the thing that goes like here and then adjoint back, that's the upper. And then the lower would be adjoint back here from the boundary map going up, adjoint back here, and then go back. So here we kind of get the same thing, but the unfulfilling thing here is that we want to just add these two things, right? But we can't really add them. And there's really no canonical way to combine these. I mean, we could take the joins of them, we could take the meets, but we don't really have a bona fide addition here.
So that's why it's not really like a true, exact copy of the traditional Laplacian.
Right. I don't think. I mean, I think there's obstructions going on, but I haven't exactly put my finger on that aspect of this work.
Cool. Thank you.
Okay, and just for anyone who wants to read our paper, here's the link. I could probably send it in the chat, maybe, or later.